Hello everyone, and thanks for watching Edupedia World videos. In this video, we are learning the basics of sets. The contents include definition, representation of sets, that is in roster method and set builder form, cardinality, subset, classification of sets, finite and infinite sets, empty or null set, singleton set, equal and equivalent sets, disjoint sets, power set, universal set, Venn diagrams, union and intersection, difference of sets, complement of a set, and properties of sets. Also, some practical problems. The study of algebra and mathematics begins with understanding sets. Sets are one of the most fundamental concepts in mathematics developed at the end of 19th century. Now let's move on to the definition. A set is a well-defined collection of distinct objects. Objects in the collection are called elements or members of the set. In mathematics, an expression is well defined if it is unambiguous and their objects are independent of their representation. Or simply we can say members of the set should be well explained. Distinct in the sense it is not likely to be repeated. Now let us move on to an example. Consider a set A equals set of all 1, 2, 3, 4 and 5. It is very common in mathematical notation to give set names. The names for set are most often given uppercase letters of the alphabet, but elements of the set are designated with lowercase letter. The name or letter is merely a convenient label and has no other meaning. Set can be represented by listing its element between French braces with elements separated by commas. Representation of a set. There are two methods to represent a set. The first one is roster form, commonly called tabular form. The second is set builder form. Now let's look into roster method. In this method, a set is represented by listing all its elements, separating these by commas and enclosing this in curly bracket. If V be the set of vowels of English alphabet, it can be written in roster form as V equals set of all A, E, I, O, U. If A be the set of natural numbers less than 7, then A equals set of all 1, 2, 3, 4, 5 and 6. Note: to write a set in roster form, elements are not to be repeated. That is, all elements are taken as distinct. For example, if A be the set of letters used in the word mathematics, then A equals set of all M, A, T, H, E, I, C, S. That is, repeated terms are only written once. Representation of set using set builder form. In this method, elements of the set are not listed, but these are represented by some common property. Let V be the set of vowels of English alphabet, then V can be written in the set builder form as V equals set of all x such that X is a vowel of English alphabet. Let A be the set of natural numbers less than 7. Then A equals set of or X such that X belongs to n and 1 less than or equal to X less than 7. Now let us consider the above example which we have already went through in set builder form. It is read as A equals set of all X such that X belongs to natural numbers and 1 less than or equal to X which is less than 7. Sometimes a vertical bar is used instead of colon, which also means the same. The symbol epsilon is used to express that an element belongs to a set. For instance, 3 belongs to set A. Its negotiation is represented by a strike of epsilon. Example, 8 dozen belongs to set A. What do you mean by cardinality? In mathematics, the cardinality of a set is a measure of the number of elements of the set. For example, the set A equals set of all 2, 4, 6 contains 3 elements and therefore A has a cardinality of 3. The cardinality of a set A may be denoted by n of A. Another important concept in set theory is regarding subset. Suppose there are two sets A and B. If every member of set A is also a member of set B, we can say that A is a subset of B denoted by A subset symbol B. Let set A be set containing all students of your school and B be a set containing all students of class 11th of the school. In this example, each element of set B is also an element of set A. Such a set B is called subset of set A. While it is true that any set is legally a subset of itself, the mathematical language has a special designation for subsets that are strictly smaller. Such a set is called a proper subset. So, for an example, while set 1, 2, 3 is a proper subset of set 1, 2, 3, 4, it cannot be proper subset of itself. In some mathematical notation, the symbol a flip U rotated 90 degrees in clockwise direction with an underline is used generally for subset, and a flip U rotated 90 degrees in clockwise direction is used exclusively for proper subset. Let's now discuss classification of sets. Sets can be classified in different forms, the first being finite and infinite. A set is said to be finite if its elements can be counted, and it is said to be infinite if it is not possible to count up to its last element. Let A and B be two sets where A is set of all X such that X is a natural number and B is set of all X such that X is a student of your school. As it is clear that the number of elements in set A is not finite, while number of elements in set B is finite, A is said to be an infinite set and B is said to be a finite set. Empty or null set. A set which has no element is said to be a null or empty or void set and is denoted by a Greek letter phi. Consider the following sets. A equals set of all x such that x belongs to R and x square plus 1 equal to 0. B equals set of all x such that x is a number which is greater than 7 and less than 5. Set A consists of real numbers, but there is no real number whose square is negative 1. Therefore, this set consists of no element. Similarly, there is no such number which is less than 5 and greater than 7. Such a set is said to be null or empty set. Singleton set. A set which has only one element is known as singleton. Consider the following set. A equals set of all x such that x is an even prime number. As there is only one even prime number, namely 2, set A will have only one element. Such a set is said to be singleton. Equal and equivalent set. Two sets A and B are said to be equivalent sets if they have same number of elements, but they are said to be equal if they have not only the same number of elements, but the elements are also the same. Consider the following examples. A equals set of all 1, 2, 3 and B equals set of all 2, 1, 3. D equals set of all 1, 2, 3 and E equals set of all A, B, C. In example 1, sets A and B have the same elements. Such sets are said to be equal sets and it is written as A equals B. In example 2, set D and E have the same number of elements, but the elements are different. Such sets are said to be equivalent sets and are written as A equivalent B. You might have noticed in the above example, the members of a set are not required to be listed in any particular order. Disjoint sets. Two sets are said to be disjoint if they do not have any common element. For example, sets A equal to set of all 1, 3, 5 and B equals set of all 2, 4, 6 are disjoint sets. Now let us move on to the concept of power set. Power set of a set is the set of all subset of the given set. Consider a set A equals AB. Subset of A are the null set, set A, set B and set AB. Here is another important question about subsets. Is the empty set a subset of a larger set? The simple answer is yes. Even though it may not look so obvious, in fact the empty set is a subset of every set. This is true because by being empty, it can contain no members that are not part of its superset. In the above example, we considered these subsets as elements of a new set, say set B. Then B equals set of all phi, set A, set B, set AB. B is said to be the power set of A denoted by P of A. Universal set. Consider the following sets. A equals set of all x such that x is a student of your school. B equals set of all y such that y is a male student of your school. C equals set such that set is a female student of your school. D equals to A such that A is a student of class 11 in your school. Clearly the set B, C, D are all subset of A. A can be considered as the universal set for this particular example. Universal set is generally denoted by uppercase letter U. In a particular problem, a set U is said to be a universal set if all the sets in that problem are subset of U. A set which is a universal set for one problem may not be a universal set for another problem. Let us discuss about Venn diagram. British mathematician John Venn introduced the concept of diagrams to represent sets. According to him, universal set is represented by the interior of a rectangle and other sets are represented by interior of circles. So, it is frequently very helpful to depict a set in the abstract as the point inside a circle or any other closed shape conveniently. Consider an example. If universal set is represented by U equals set of all 1, 2, 3, 4 and 5. Suppose A equals set of all 2, 4 and B equals set of all 1, 3. Then these sets can be expressed like this. This diagrammatical representation of set is known as Venn diagram. Let us now discuss some of the application of Venn diagrams. Venn diagrams are used in mathematics, logics, theological ethics, genetics, study of Hamlet, linguistics, reasoning, and many other areas. Union and intersection. In set theory, the union of collection of set is the set of all distinct elements in the collection. It is one of the fundamental operations through which sets can be combined and related to each other. Example, A union B. Particularly, the union of two sets A and B is the set containing those elements which are elements of A or elements of B. Consider the following example. A is a set having all players of Indian men cricket team and B is set having all players of Indian women cricket team. Clearly, A and B are disjoint sets. Union of these two sets is a set having all players of both teams and is denoted by A union B. Here, the union consists of all points which are colored blue or red. Take another example. D is a set having all players of cricket team and E is the set having all players of hockey team of your school. Suppose 3 players are common to both the team, then union of D and E is a set of all players of both the teams, but 3 common players to be written only once. Here, the union consists of all the points which are colored blue or red or purple. The purple colored region illustrates the intersection which we are going to deal next. Intersection of sets. If A and B are two sets, then the set of those elements which belong to both the set is said to be the intersection of A and B. Consider the sets A equals set of all 1, 2, 3 and 4 and B equals set of all 2, 4 and 6. It is clear that there are some elements which are common to both the sets A and B. The set of these common elements is said to be the intersection of A and B and is denoted by A intersection B. Here A intersection B is set of all 2, 4. Remember, if A and B are disjoint sets, then A intersection B is a null set. Difference of sets. Consider the sets A equals set of 1, 2, 3, 4 and 5 and B equals set of all 2, 4 and 6. A new set having those elements which are in A but not in B is said to be the difference of sets A and B, denoted by A minus B. Here A minus B equals set of all 1, 3 and 5, that is, deleting the common elements of A and B from set A. Similarly, set of those elements which are in B but not in A is said to be the difference of B and A. It is denoted by B minus A. Here B minus A equals set 6. In general, if A and B are two sets, then A minus B equals set of all x such that x belongs to A and x does not belongs to B. Similarly, B minus A equals set of all x such that x belongs to B and x does not belongs to A. Difference of two sets can be represented using Venn diagram like this. Now let us move on to complement of a set. If U is the universal set and A is its subset, then the complement of A is a set of those elements which are in U and which are not in A. It is simply denoted by A prime or A with a superscript C. So A complement equals universal set minus set A, which is written as set of all x such that x belongs to U and x doesn't belongs to A. Complement of a set can be represented using Venn diagram like this. To get a better view, let us consider an example. Let X denote the universal set and Y and set its subset, where X equals set of all x such that X is any member of the family. Y equals set of all x such that X is a male member of the family, and set equals set of all x such that X is a female member of the family. Now, X minus Y is a set having female members of the family, and X minus Z is a set having male members of the family. X minus Y is said to be the complement of Y and is usually denoted by Y prime or Y complement. X minus Z is said to be the complement of Z and denoted by Z prime or Z complement. Before going further, let us have a look into some important points. Difference of two sets can be found even if none is a subset of the other, but Complement of a set can be found only when the set is the subset of some universal set. It is obvious that complement of a null set is the entire universal set. Its converse is also true. Complement of a universal set is the null set. Now we shall discuss some properties of sets. With any operation that we have in mathematics in general, we usually have a set of properties that is pretty easily confirmed or derived from the operation itself. That goes just the same with set operation also. The set operation verifies the following operation. Associative law. It states that the way we associate or we put the parenthesis doesn't change what is in the set. Or we can say A union B union C is same as A union B union C. Similarly, A intersection B intersection C is same as A intersection B intersection C. Commutative law. This law means that the element can commute around the operation. That is, A union B is same as B union A. Similarly, A intersection B is same as B intersection A, or simply the order is not important. So far we have seen single operation being done. Now once we start mixing operation, it becomes a little more complicated, and that's why distributive law click in. In distributive law we can say that A union B intersection C equals A union B intersection A union C. Similarly, A intersection B union C is same as A intersection B union A intersection C. Identity laws. It states that A union, the null set, is the set A itself. Similarly, A intersection, the entire universal set, is the set A. Complement laws. It states that A union A complement is the entire universal set, and A intersection A complement is empty set. Idempotent laws. It states that A union A is the set A itself, and A intersection A is also A. Now let us move on to De Morgan's law. In propositional logic and Boolean algebra, De Morgan's laws are a pair of transformations rules that are both valid rules of inference. They are named after a British mathematician, Auguste De Morgan. The rule can be expressed in English as the negation of a conjunction is disjunction of the negation, or informally as not A and B is same as not A or not B. So A union B, the whole complement, is A complement intersection B complement. That is, everything not in A or B is same as everything that not in A and not in B. Now let us do some practical problems based on sets. Now consider a set A. Let A equals set of all x such that x belongs to z plus. Z plus is nothing but set of positive integers, and less than or equal to 5. Similarly, let B equals set of all y such that y is a prime number. y is a prime number which is less than, say, 10. Okay, now let's find A union B and represent the same using Venn diagram. So this is the question. Now let's find the solution. We have A equals set of all 1, 2, 3, 4 and 5, because these are the positive integers less than or equal to 5, and B equals set of all 2, 3, 5 and 7, prime numbers less than 10. Now we have A union B equals set of all 1, here is 1, then 2, 3, 4, 5 and 7. Here we shall not consider repetition, so I have already written 1, 2, 3 and 4 here, so I need not write them again. So this is A union B. Now let us represent the same using Venn diagram. For that, let's consider universal set U. This is set A and this is set B. Since A and B have common elements, that is 2 and 3, also 5 are common, so they are not disjoint. So let's make them intersect. Set A contains numbers 1, let's write 2 here, 3, 4 and 5. And similarly, set B contains numbers 7, because 2, 3 and 5 we have already written here, and this is common to B also. So this is the solution. Take another question. Let A and B be two finite set such that n of A equals 20. N of A equals 20 and n of B equals 28. N of B equals 28, and also n of A union B equals 36. N of A union B equals 36. We have to find n of A intersection B, that is n of A intersection B. Solution. Using the formula, n of A union B equals n of A plus n of B minus n of A intersection B. N of A union B equals n of A plus n of B minus n of A intersection B. We have n of A intersection B equals n of A plus n of B minus n of A union B. If we substitute this value in this equation, we have n of n of A intersection B equals 20 plus 28 minus 36, which is equal to 12. Let us do one more problem. If n of A minus B equals 18, n of A union B equals 7070, and n of A intersection B equals 25. Find n of B. Solution. Using formula, n of A union B equals n of A minus B plus n of A intersection B plus n of B minus A, we have 70 equals 18 plus 25 plus n of B minus A. From this we can calculate the value of A minus B. So A minus B equals 70 minus 43, which is equal to 27. Now n of B equals n of A intersection B plus n of B minus A. Hence the value of n of B is 25 plus 27, which equals 52. Hope this video helps you to have some better idea about set. For more videos, please follow Edupedia World. Thanks for watching.